Now that we have introduced general exponential functions, we're going to introduce general logarithm functions as their inverse functions. Specifically, we have seen in the previous video that if we fix a number a to be the base for an exponential, so this number a has to be positive and different from 1, then the corresponding function a to the x, the exponential of base a, is a one-to-one function whose domain is the entire real line and whose range is the positive reals. Because it's one-to-one, it has an inverse function that we're going to denote by log a, the log of base a, and of course it has domain the positive reals and range all the reals, and it is defined with the usual formula that we use to define inverse functions. In other words, the log of base a of x is y, if and only if x is a to the y. What that means is that the log of base a of x is the power to which we have to raise the base a in order to get x. So this function, log a, is called logarithm of base a, and a particular case we've studied before is the case of base e, where e is the Euler number, and then we get the natural logarithm. Of course, what matters here is this formula that defines inverse function, and because the log of base a and the exponential of base a are inverse of each other, it means that if I raise a to the power log a of x, as long as this expression is defined, that is when x is positive, it returns x. And similarly, if I plug a to the x inside the log of base a, it returns x. Now I said that the log of base a of x is the power to which we have to raise the base a in order to get x. So let's look at some examples here. What would be the log of base 5 of 25? Well, the question is, to what power do we have to raise 5 in order to get 25? To the power 2, because 5 squared is 25. In other words, the log of base 5 of 25 is 2. What would be the log of base 4 of 2? In other words, to what power do we have to raise 4 in order to get 2? This would be to the power 1/2, because 4 to the 1/2, that's root of 4, it is 2. What would be the log of base 2 of 1/2? In other words, to what power do I have to raise a number 2 in order to get 1/2? Well, 1/2 is 2 to the negative 1, in other words, this log of base 2 of 1/2 is negative 1. Okay, so let's look at the graphs of these logarithms of different bases. Here is a graph of 2 to the x, right? In other words, the exponential function of base 2. And we have seen in the previous module, when we were talking about inverse functions, we've seen how to obtain the graph of the inverse function of a one-to-one function. What we do is look at the line y equal x and take the reflection of our one-to-one graph with respect to y equal x, and that's going to give us a graph of the inverse function. In other words, the graph of the log of base 2 of x is going to be obtained this way by reflection about y equal x of the graph of 2 to the x. And so this is what it looks like. Because 2 to the x goes to 0 when x goes to negative infinity, that means that the log 2 of base x, the log x of base 2 goes to negative infinity when x is approaching 0 from the right. And then you see that this is a concave down increasing function with limit infinity. Now in the case where the base is less than 1, say for instance we look at the exponential of power 1/3, well, we can obtain the inverse function in the same way. Consider the line y equal x and take the reflection about this line of the blue graph. We obtain this red graph, which is the log of base 1/3. So the case where the base is between 0 and 1. And you see that in that case, as x is approaching 0 from the right, the values of the log are going towards positive infinity. And on the other hand, when x is going towards positive infinity, then the log is going towards negative infinity. Now in general, we may look at how a change in the base affects the graph, the shapes of the graphs. And now I'm going to play a little animation where we have in blue the graph of the exponential of base A, and in red the graph of the logarithm of base A. And on the x-axis we're going to have a dot that represents the value of A, starting to a value very close to 0, and then A increases. So we're going to start with a value of the base that is close to 0, and therefore corresponding to the kind of case we are looking at right now. In other words, the exponential function is decreasing with a limit of 0 at positive infinity, and the logarithm has a limit of positive infinity near 0. And then we're going to increase the base and see what happens. Again, the red graph is the logarithm, the blue graph is the exponential with the same base. Turning to the question of how these logarithms are related to each other, one practical question that you may ask yourself is, how do I calculate, I don't know, the log of base 3 of 7? If you look at your calculator, you'll see that you have two keys for logarithms. One denoted ln, and this is a natural log, and another one denoted log, and this is a convention that this is the log of base 10. So how do we calculate the log of another base, let's say of base 3 or 7 or something like that? Well, we can do that, and we don't need any other key, because the log of base A of x is really just proportional to the natural logarithm of x. And the coefficient of proportionality is just the reciprocal of the natural log of the base. So let me try to justify this. Let's start with the expression that y is the log of base A of x. So what we want to do to establish the formula is to obtain y in terms of ln of x. First thing we're going to do is write what that means. Right? We define this logarithm of base A as the inverse of the exponential of base A, so that means x is a to the y. And then I'm going to, because I want to express that in terms of natural logs, I'm going to take the natural log on both sides of this equality. I get natural log of x is the natural log of a to the y. And we know that for the natural log, one of the logarithmic laws is that if I have natural log of a power, I can pull out the exponent as a multiplicative constant in front. So this is just ln of x is equal to y multiplied by ln of a. But what I want is express y, so I just solve for y and I get ln of x over ln of a. But y was really just log of base A of x. So that establishes our formula. Now this formula gives us as an immediate corollary that all the laws of logarithm that we've seen for the natural log extend to this more general logarithmic function. In particular, so if we pick a base A, that has to be positive and different from 1, and two x and y's that are both in the domain, in other words positive, of the log of base A, we have that the log of a product is the sum of the logs, log of a quotient is the difference of the logs, and that log of a power, I can pull out the power, pull out the exponent as a multiplicative constant, just like we have seen for the natural log. I said it's an immediate corollary of the change of base formula that we just have seen, and I won't go over that in details, but just to justify this this statement, let's look at the first logarithmic law. And let's try to prove it. So we start from the left-hand side, the logarithm of base A over product, and we write out what it means in terms of the change of base formula. So it's just a natural log of xy divided by a natural log of A. This 1 over ln of A is just a multiplicative constant, and then at the top I have natural log of xy, which we know is natural log of x plus natural log of y, because we've already established these formulas for the natural log. So we obtain ln of x plus ln of y over ln of a. So that's ln of x over ln of a, which is log a of x, plus ln of y over ln of a, which is log a of y. And so that establishes the first formula. As you see, this is just using what we've already established for the natural log, and the other two formulas would follow just as easily. So we have these laws of logarithm, and that means that we can manipulate at least some expressions that contain logs. For instance, if we're trying to evaluate the log of base 8 of 320 minus the log of base 8 of 5, it's a log of the same base, it's a difference of two logs of the same base, and therefore, using the second formula in the laws of logarithm, this is really the log of base 8 of the quotient 320 divided by 5. The 320 divided by 5 is 64. Now we have the log of base 8 of 64. Now what is that? This would be the power to which I have to raise the number 8 in order to get 64. But since 8 squared is 64, that means this log is just 2. Just to look at a second example, let's say we want to evaluate 10 to the log 10 of 4 plus log 10 of 7. In the exponent, I have a sum of logs of the same base, and therefore, using the first formula, it's really just a log of the product. In other words, what I have is 10 to the log of base 10 of 28. But now I have an exponential of base 10, in which I'll plug a log of base 10, and these functions are inverse of each other, so I obtain simply 28. Now let's turn to the question of the derivative of the log of base a. The change of base formula gives us immediately what the derivative would be, because now it's the derivative of ln of x divided by ln of a, and ln of a at the bottom is really just a multiplicative constant, so I can pull out 1 over ln of a, that's a multiplicative constant, and I multiply by the derivative of ln of x, which is 1 over x, so I obtain 1 over ln of a times x. And now we can try to apply this formula, for instance, to differentiate the log of base 5 of x divided by x minus 1. Now in that case, we may want to simplify this before we differentiate, because if we differentiate, we know that differentiating quotients can be complicated, and there is a quotient inside the log, whereas differentiating sums or differences are easy. And one advantage of the logs, as we have seen when we were talking about logarithmic differentiation, is that it transforms products into sums and quotients into differences. So we can rewrite that as the log of base 5 of x minus log of base 5 of x minus 1, or 1 over ln of 5 multiplied by the difference of the natural logs. Now one caveat here, I'm rewriting the same expression here. What I'm leaving under the carpet is that the left-hand side and the right-hand side don't have the same domain of definition, so the equality is a little bit of an abuse. That's assuming that x and x minus 1 are positive. In other words, that x is positive. That x is greater than 1. And so for x greater than 1, we have this equality. However, you see that what's inside the parenthesis on the left-hand side, right? I have x over x minus 1. To plug that in the log of base 5, all I need is this quotient of x divided by x minus 1 to be positive. And that could happen if x and x minus 1 are both negative. So in particular, if x is negative, then x and x minus 1 are negative, and the left-hand side would still be defined because the quotient would be positive. On the other hand, the right-hand side would not be defined. So again, we have equality here with the caveat that this is the equality when every term is defined, in other words, for x greater than 1. So now we have rewritten f in a form that is easier to differentiate, and now when we differentiate, we have this multiplicative constant 1 over ln of 5, and then we multiply that by the derivative of ln of x, which is 1 over x, minus the derivative of ln of x minus 1, which is 1 over x minus 1. Looking at the integral side of things, here an integral that doesn't really use logs of different bases, but rather exponentials of different bases. we want to find an antiderivative of 2 to the x divided by 2 to the x plus 1. One thing that you may note is that if you take 2 to the x plus 1 and you differentiate that, you get 2 to the x, because the derivative of 1 is 0. So because of this observation, it makes sense to try a substitution where we take for the new variable u 2 to the x plus 1. Then du is simply the derivative of 2 to the x, which is 2 to the x multiplied by ln of 2, times dx. What we have inside the integral is not 2 to the x ln of 2 dx, but simply 2 to the x dx. So we solve for that, and 2 to the x dx is 1 over ln of 2 du. So now I'm going to replace in the integral the top 2 to the x dx by 1 over ln of 2 du, and the bottom by u. And so we obtain 1 over ln of 2 multiplied by the integral of du over u. But we know what that is. That's the natural log of absolute value of u, which in our case, because u is a positive function, is really just ln of u. And so we obtain natural log of 2 to the x plus 1 divided by natural log of 2 up to a constant. Let's look at a second example where we're trying to calculate an integral that this time depends on a logarithm of a different base, in this case of base 2. So we have the integral of the log of base 2 of x divided by x. Now we've seen that the log of base 2 is simply proportional to the natural log, and therefore its derivative is also proportional to 1 over x. So what we have at the bottom, we have x at the bottom, but that corresponds to 1 over x, which is proportional to the derivative of the log of base 2. So this observation leads to the introduction of the new variable log of base 2 of x. When we calculate du, we obtain 1 over x ln of 2, which is the derivative of log 2 of x, multiplied by dx. What we have in the integral is not 1 over x ln of 2, but 1 over x. So we solve for dx over x, and this is ln of 2 du. So we're going to replace dx over x by ln of 2 du, and log of base 2 of x by u, and we obtain ln of 2 multiplied by the integral of u. Of course, an antiderivative of u with respect to u is u squared over 2, and so we obtain ln of 2 divided by 2 multiplied by the square of the log of base 2 of x, and this is up to a constant. Now let's turn to the next video to look at other kinds of transcendental functions, in particular inverse trig functions.